Hi, everybody. Welcome to Fiveable Cram Previews. This is our second physics cram. Let's wait a little for everybody to start coming in. All right. Thank you all for coming to Fiveable Crams. We're going to get started now. And welcome. Let's move on to the next slide. All right, so before we get into the meat of the previews today, we're going to be talking a little bit about the crams. So if you're considering buying a cram pass for $15, here's the schedule for AP Physics. So on May 6th, we'll be going over units 1 and 2. On May 7th, 3 and 4. On May 8th, units 5 and 6. And on May 9th, we have unit 7. And May 10th, we're just going through all of the units once again. Now, all of these crams will be packed with a lot of content and what we're all looking for, which is a lot of practice as well. And the people you see on the right are your student hosts for these crams, and you'll be meeting them today as well. Let's get started. So my name is Tammy Matthews.
It seems like Juliana has some mic problems, but hi everyone, my name is Shagun and I'll be introducing the Work-Energy Theorem later on. So excited to meet you guys.
Hi everyone, my name's Zeke and I'll be going over kinetic energy with you guys today.
Hello, my name is Juliana and I'll be going over Intro to Energy and Energy Basics.
All right. Okay, guys, don't forget to follow. Oh, Anastasia, do you want to introduce yourself?
I'm Anastasia, and today I'll be going over potential energy.
All right, thank you. So don't forget to follow @ThinkFiveable on all social media platforms, TikTok, Instagram, YouTube, LinkedIn. We post great opportunities, so don't miss out on any of that. Next slide. All right, so this is some more information on how you can make the most of a cram preview or one of those cram, the 5-day things. Number 1, you can take notes. Number 2 is you can make use of the Cram Hub. So it has all the slides, review packets, and replays. So you can rewatch and stuff. Also the group chat. The group chat is for sharing tips and tricks to participate when we ask questions. And this is really helpful. You guys can help each other. And finally, the Q&A tab is just for asking questions to the student host. You can utilize this to ask any questions about physics or about like the FRQ designs, or even, getting ready for a test and how to really ace that. Also, the replays are available immediately after each event. So yeah, let's move on to the next slide. Yeah, here's some community agreements. Let's be supportive, patient, and kind, and to really ensure all of our success. Next slide, please. All right, this is the final thing. You can win $100 by sharing your Cram experience on TikTok or Instagram. So this is something available to the people who buy that $15 Cram pass. What you have to do is you have to make a video, a funny one, and you can use the hashtags Fiveable Crams and tag @ThinkFiveable on Instagram and TikTok. And also you need to make sure your account is public and you make sure you follow Think Fiveable. And you will be notified via DM from Fiveable's official account. So yeah, it's a fun opportunity. Let's move on to the next slide. All right, so coming into what our Cram previews are all about, today we'll be talking about the Work-Energy Theorem. Next slide, please. All right, this is our agenda. So we'll be starting off with intro to work, moving on to intro to energy, really diving into the types of energy, so kinetic and potential. And finally, we'll be talking about the Work-Energy Theorem. So yeah. Oh, also we'll be having a quiz at the end, so stay tuned for that. All right, next slide. Okay, let's get started on intro to work. Next slide. So work is defined as the energy transferred when a force is applied over a distance. So for example, when you lift a box, you're doing work on that box. So the amount of work you do depends on two things. So the force you apply and the distance over which you apply it. Next point is that work is a scalar quantity. So that means work has magnitude but no direction. So basically what it does, it represents the amount of energy transferred, but it doesn't tell you anything about the direction in which that energy is transferred. Next point is that a force distance graph, the area under that, can tell you, it will give you the amount of work done, and that's in joules. Let's move on to the next slide. All right, this one is that work can be positive, negative, or zero. So to really understand this, let's look at the formula on the left side of the screen here. So we have work is equal to FD cosine theta. So W is equal to work, obviously. F is equal to force. D is the displacement over which that force is applied, and theta is the angle between the force and the displacement. So when force and displacement are in the same direction, positive work is done. So for example, if I push a box across a room, the force I apply is in the same direction as the displacement that box moves. So therefore, I can say the work that I do is positive on that box. Now, on the other hand, if the force and displacement are in opposite directions, negative work is being done on the object. So for example, if I try to push that box uphill, right? The direction of displacement is downward, and while I'm trying to push uphill, and these directions are opposite, making the work done on the box negative. And finally, there are two instances when zero work can be done on an object. So instant one is when there's no net displacement. So that is if an object is subject to a force, but there's no net displacement in the direction of the force, the work done is zero. So for example, if you push a wall, right? You can push and push and push, but it's not going to move because you don't have enough force to make that wall like displace itself. So we can say that there's zero work done on the wall. The second time when we can have zero work done on an object is when the force and displacement is perpendicular to each other. So for example, if I hold a book in my hand and I move it to the side, we can say that the work done on that object is zero because the displacement, I'm moving it this direction. So the displacement is horizontal. However, the force is upward, making like kind of displacement or perpendicular vectors between the two. And I can say that because if you look at the formula of force times displacement times cosine theta is 90 in this situation with the book and the force. And cosine 90 is equal to 0, making the object have experienced 0 work. Hope that made sense. I see a couple of messages. Let me look. Okay. Okay, I don't see any questions. So let's move to the next slide. So we have a practice question here. It is a boy pulls a 10-kilogram box across an ice rink for a distance of 50 meters. He exerts a constant force of 10 newtons on a rope attached to the box at an angle of 60 degrees. How much work has he done on the box? So take a minute, and once you get an answer, feel free to put it in the chat. Okay, I see D. Do you have any other options? Okay, more D. All right, perfect. So this seems like a pretty straightforward problem. Yes, I see option D is the very popular one. Oh, okay, I see E as well. Right. So yeah, I think majority of you guys are correct. This is a pretty straightforward problem. Let's get those transitions in. So we know our work formula. It's force times cosine theta times displacement. And all we're doing is basically plugging and chugging, right? So let's next transition. So we just have our 10 newtons. We have our cosine 60 because that's the angle. And we have our 50-meter displacement. And we finally multiply all of that together and we get, yes, 250. 250 joules, which is option D. So great job, guys. You did an amazing job. So let's move on to Intro to Energy, and I'm handing it over to Zeke.
Hello, I'll be covering Intro to Energy today for you. Next slide, please. All right, so the definition of energy is the ability or the capacity to do work. So the two topics of work and energy are very closely related. So first we'll talk about system basics. So energy can either be in a closed system or an open system. The difference is that in a closed system, the amount of energy that is in the system stays constant, it doesn't change. And in an open system, energy can either leave the system or get added to the system. And the way that energy is added to an open system is through work. Work is the only way that energy gets transferred across systems. Also, in a system, there is something called mechanical energy, which is kinetic plus positional energy. And in most systems in AP physics, you're going to deal with constant mechanical energy, which means you're only taking kinetic and positional energy into account, and you're not really accounting for the force of friction or chemical forces or other forces unless a problem tells you to. Also, something to remember is that in a closed system, no outside forces will act on objects inside the system. So basically, the three general categories of energy are kinetic, positional, and non-mechanical. Kinetic energy is displayed through movement, and the formula that we use is mass times velocity squared divided by 2. Positional energy comes in multiple forms, and the most common types on the AP Physics 1 exam are elastic and gravitational, and they all relate to the actual position of the object. For elastic, the equation we use is the spring force times the displacement squared divided by 2. And for gravity, the equation we use is mass times the force of gravity times the height. And then finally, the third type, which you're not going to see very often in AP Physics 1, are chemical and thermal energy. And these are types of energy that aren't included in mechanical energy again, so they're not given formulas on this AP exam. All right, next slide, please. Okay, so we have a practice question here that we will set up a poll for. And the question is, a planet orbits a star X. Which of the following systems can be considered a closed system? And feel free to either type your answers in the chat, or we will be setting up a poll for you. All right, the poll should be visible now. And I'm looking at the chat right now. Let's see here. I'm seeing a lot of B's, some A's, a lot of B's. All right, so to answer the question, B is the correct answer. So when a planet orbits a star, that means that both the planet and the star are enacting a gravitational force on each other. And if there are forces acting on each other, that means both objects have to be in the system to be considered a closed system. If it was just the planet, the gravitational force from the star would be removing energy in the form of the gravitational force, and vice versa if it was a system with just the star. All right, and then for kinetic energy, Zeke will be talking about the problem.
Hi guys, so I'll be going over kinetic energy with you today. Let's go to the next slide. So the equation for kinetic energy is going to be 1/2 the mass times the velocity squared. Kinetic energy is a part of the work-energy theorem, and it's the energy an object has when it is moving. It is important to note that velocity is going to have a more significant effect on kinetic energy than mass. And a lot of questions you're going to see about kinetic energy are going to be things like roller coasters and ramps. And another very common question that you're going to see that has to do with roller coasters and ramps is it's going to give you points on that different chart, and it's going to ask you which has the largest kinetic energy, and it's always going to be the lowest point in height. Let's move on. So based on what I just said, I have this practice question for you guys to do. I do not want you guys to use put your answers in the chat, though. I'm creating a poll right now, so please wait to put your answers in that. Okay, I'm going to give you guys a couple seconds to do that now. I'm going to wait for a couple more of you guys to answer. Just try your best. Okay, we're gonna, let me turn that off. Make sure that you guys are answering on the whale and dolphin question. Okay, so I'm gonna reveal the results real quick. So most of you guys put A, which that is the correct response, but it looks like we also had quite a bit of you guys put B, and a couple of you guys put C. So let's go to the next part on this slide so we can show you how we did it. Okay, so the first thing that you guys have to remember is that kinetic energy is 1/2 the mass times the velocity squared. So in the question, it tells you that a whale has 4 times the mass of a dolphin, and it's moving with twice the speed of the dolphin. What we're going to do is we're going to use kW to symbolize the whale, and what we're trying to do is figure out what the dolphin would be compared to the whale. So you see, remember, kinetic energy equals 1/2 mass times velocity squared. And then we also pulled out that the whale has 4 times the mass and twice the speed of the dolphin. So we can use that, put that in our equation, and with these types of questions, just plug in numbers and chug. You don't have to have like a full-on number like mass is 1. You can just plug in numbers to get an answer. So you see for the whale that we just plugged in 4m and then 2v squared. And the dolphin, we just plugged in the m and then the velocity squared. We can cancel out the 1/2 since it's a common variable between the equations. That means since they both have the same thing, we don't really need to keep that when we're solving for this. And then what we did is we assumed values of 1. This is what I was saying. Just plug in a number to get an answer. You don't have to know the exact mass. You're just trying to plug something in because we already have a ratio of 4 mass to 1 mass and 2 velocity to 1 velocity. So we plugged in 1, and when we do that for the whale, you would get 4 times 1, that's 4. When you plug it in for the 2 velocity squared, you would get 2 squared, that's 4. 4 times 4 is 16. And whenever you plug in 1 for the mass of the dolphin and 1 for the velocity of the dolphin, that's just 1 times 1. So we end up getting a relationship of 16 to 1, and that is why our answer is A. Okay, hopefully that helped, and I'm going to pass it on to our next presenter.
So right now we will be talking about potential energy. Next slide, please. So potential energy is the stored energy that an object possesses due to its position. So gravitational potential energy, for example, is the energy of an object due to its height above some reference position, usually the Earth's surface. An important thing to note is that position is going to be relative. So you can choose which point you want to make your zero, as long as you stay consistent. Next slide, please. So the gravitational potential energy is energy that an object possesses by virtue of its position in a gravitational field. So this is the energy that is stored as a result of a vertical position or the height. It is also stored as a result of the gravitational attraction of Earth as for an object. So the equation for potential energy is going to be mgh, which is mass times gravity times height. And where PE stands for the gravitational potential energy, M is the mass, G is the acceleration due to the gravity, and H is the height or the elevation of an object above the reference point. So this formula assumes that the gravitational field is constant over the distance h. It's important to remember that if the gravitational field is not constant, then the formula becomes more complex, and it really just depends on the distance between the object and the source of the gravitational field. Next slide. So the elastic potential energy is the potential energy that is stored as a result of applying a force to deform an elastic object. So the elastic potential energy depends on the amount of deformation or stretching that also occurs. So properties of the material the object is made affects the energy that is stored. And the equation for elastic potential energy is going to be 1/2 kx squared. Next slide, please. So do this practice question, and there's going to be multiple answer choices for this practice question, so you can type your multiple answer choices in the chat. So I'm seeing a lot of you guys are putting in B, C, and E. These all look like the correct answer choices, so let's go through this problem. So a heavy dart and a light dart are launched horizontally on a frictionless table by identical ideal springs. Both springs were initially compressed by the same amount. Which of the following statements about these darts are correct? There could be more than one correct choice. So let's read A. The darts both have the same kinetic energy just as these move free from the spring. So energy is always conserved, so the darts will have the same amount of kinetic energy. So this will be the right answer. B. The lighter dart leaves the spring moving faster than the heavy dart. So the lighter dart has the same energy as the heavier dart. So the less mass means it will have to make this up with having greater speed. So this is also a correct choice answer. C. The heavy dart had more initial elastic potential energy than the lighter dart. So this is not true because they both start off with having the same amount of compression in the beginning, so they will have the exact same amount of elastic potential energy. So C is not the right answer. D. Both darts move free of the spring with the same speed. This is not true because as we discussed, because they will have the same amount of kinetic energy, the lighter dart will have to be moving faster in order to make up for the amount of kinetic energy that they will both have to make them equal to each other. So this will not be the correct answer. E is both darts had the same initial elastic potential energy. And this is true because as the problem stated, they both start off with the same amount of compression. So the answer to this problem is going to be A, B, and E. And I will be passing it on to the next speaker now.
All right. Hi, everyone. I hope you guys are doing good. You guys made it to the halfway mark and we're almost there. So I'm hoping you guys are getting a lot out of this Cram preview. So next, we're going to be talking about the star of the show, the Work-Energy Theorem. All right, so what is a work-energy theorem? So you might see this several different ways on several different sheets or whatever your teacher sent you. But one of the most common forms of writing the work-energy theorem is that the net work is equal to the final kinetic energy minus the initial kinetic energy. And sometimes you also might see that it's just listed as the net work is equal to delta kinetic energy, and that just basically means final minus initial. So the work-energy theorem basically states that if you just think back to matter and those laws, that you can never destroy or create energy. So you're always just transferring one energy to another. And that transfer of energy requires work. So basically you're saying that if you're running at some kind of speed and you move faster, that process of going faster and raising your speed, that requires work. So the work-energy theorem states that the total work done is the difference of the final kinetic energy and the initial kinetic energy. So you always want to make sure that you can use this relationship in order to identify, for example, what speed you need, the mass you need, and you can identify that you have all these possible values in order to finally answer the question. And you're going to see this pattern a lot throughout AP Physics 1. I just posted the reference sheet a while ago back in the chat, but you can see that all the equations necessary on the exam that you need to pass and to get a 5 are on there. So if you're able to understand which equations to use on the exam and which time, you can easily be able to manipulate the equations and be able to identify which variables you need and which ones you need to solve for. So the neat thing about the work-energy theorem is that you can relate this to the definition of work, which Tammy talked about before earlier on, which is work is equal to the force times displacement. So you can equate that the change in kinetic energy is equal to the force times displacement. And this is a very powerful theorem because over here you have so many different relationships and unknown variables you can solve for. And that helps you solve those really tough physics problems where you're given, for example, acceleration, mass, and velocity, and they're asking you, for example, for displacement. Well, if you see and break down this theorem, you can see that you have most of these variables and you just need to solve for displacement. So you can use this relationship in order to find the relationships between work, speed, mass, and distance. And I'm not going to reveal anything right now, but you can also use a lot of kinematics, force equations, free body diagrams. All those topics really come together because we're equating force and distance with energy. All right. So just to make things a few clear on what's positive work, what's negative work, and how this affects the work-energy theorem. So doing work on a system increases, which is positive work, or decreases, which is negative work, the energy that a system has. So usually on the AP Physics 1 exam, if you have a negative sign associated with work, that usually means you're doing negative work on the system. And that just essentially means that whatever object you have, the work is happening in the opposite direction. So you're not actually doing any positive work. You're actually, for example, doing negative work. So one really common example of this is that, for example, if I have a book and I raise that book up, you're actually doing the positive work because you're actually moving with the work's displacement. So doing work on a system increases the energy of that entire system. However, when a system does work, you're actually losing energy. So if you just think about that kind of like in common sense, that makes sense because, for example, as humans, when you do work, you get really tired, so you're losing your energy. That's how I like to think of it. But when, for example, you're like sleeping, I like to think of that you're doing like work on your brain because you're letting your brain rest. So that means you're like gaining energy. So a common mistake in the work-energy theorem is that many people associate that this theorem is associated with just the work of a specific object, for example, like a book or just something that's not that's not completely isolated from its system. And that's not actually true, because when you're thinking about an object within the context of an entire system, the work energy theorem actually applies to the total work done between that system. That's a network. You're not specifically talking about a specific object or the work done by that singular force. Another mistake that a lot of people make is that a really important tip that I would say is that when you're equating work and energy and force together, you always want to draw your free body diagrams for these objects, because you can see that there's multiple forces that usually occur on one object. And especially in the AP Physics 1 exam, they're not going to make it that easy for you, where you have where you only have one force acting on an object. So once you draw your free body diagram, you can really be able to understand which forces only act on that specific object. And then you have to really do a analysis of how those forces contribute to the overall work and the network of their object. So if you look on this specific image over here that I have on the right, if I have a box and I'm moving it to the right, and my displacement, since the velocity is going to the right as well, the box is moving to the right. So if you think back to the theorem, it's work is equal to force times displacement times cosine theta. Now, the cosine theta is applicable to the angle between the force and the displacement. So if the force is going to the right and the displacement is going to the right, then there's no angle between them. So therefore, the angle is 0. So if we think back to our trigonometry, cosine 0 is 1. Therefore, that object is doing positive work as it moves in that direction. However, for example, if you have some friction, or the net force is just moving in the opposite direction of the velocity, then displacement is going that way, but the force is going that way. So that total angle between the force and the displacement is 180 degrees. And cosine 180 is -1. So therefore, that object is doing negative work. All right. So to just sum up what we just talked about, I have a little practice question over here. I almost revealed the answer before when I was doing that book example, so I don't know if you guys caught on to that, but I'll give you guys a few minutes to solve this problem, and I'll put up a poll really quickly so you guys can put your answer on there. All right, so I see a few answers on here. I'll just wait like a minute more and then I'll go on to the next answers. I see mainly B's and I see an A. All right, so I see mainly B's now. I see one C, but you guys are right. The answer is B. The work is negative on the way up and positive on the way down. That's good because it looks like you guys grasp the concept really well. So that's true because if we think about what gravity is, like I said, if you have that object and you create your free body diagram, gravity always acts in the downward direction. So therefore, our force is downwards. So when the ball is going up, our force is downwards, but the displacement over our ball is upwards. So that makes a cosine angle of 180 degrees, and that would produce negative work. So whenever work is done in the opposite direction, the work done is negative. However, when the ball comes down, it moves in the same direction as gravity. So therefore, there's no angle between the force and the displacement. So therefore, the work done is positive. And mathematically, if we want to think about it, just look at the actual description of cosine 180 and cosine 0. Now, it's really important to note that you guys understand that angle is really between the force and the displacement. So sometimes you might have this work problem done on a ramp, and that ramp is so some people get confused, and when they're asked to find the work of, for example, that object moving down or up the ramp, they confuse that angle and put the angle of the ramp there. However, you should know that angle is the angle of the incline of the ramp, and that has nothing to do with the angle between the force and the displacement. So you always want to make sure, what I do is that when I draw my forces out, then I make like a little angle between, okay, what's my displacement and what's my force, since those are the two vectors you really want to think about. All right. So here we have another practice question. Yay. So here, this is more, it's not a multiple choice question. It requires, I would say, if you have a pencil or a calculator nearby and a piece of paper, just grab that. And then I'll give you guys like a few minutes to solve these questions. But essentially, you have a 15 kilogram mass that has its speed changed from 10 meters per second to 30 meters per second in 8 seconds by a constant force. So the two questions I want you guys to answer are, A, how much energy does the object gain? And B, what is the magnitude of the constant force? So here you really have, for part B especially, you really have to connect all those concepts of kinematics, dynamics, and work and energy together. So let's see how you guys do with that. And the main thing is that on the AP Physics 1 exam, you have 90 minutes to do these 4 questions. And each question is definitely more than 2 parts. So while the recommended time for each of the FRQ questions is about like 22.5 minutes, I would say I'd give you guys like 5 to 7 minutes to solve these questions. Let me know if you guys need more or less, but I do want to get ahead with the cram preview so you guys have time for the quiz. I'll give you guys like a minute more-ish to solve this problem. It might be challenging at first to relate all the topics, so just let us know if you guys need any help. And once you find an answer, then you can put it down in the chat. right, so I see an answer. And all right, so that seems a very promising answer. Let's go through parts A and B. So yes, you were right. It was 6,000 joules. So let's just go over how to solve part A in case you were a little bit stuck. So this is just simply just applying the work-energy theorem. So if you think about, just break down this problem, you see that you always want to write down the quantities that you're given. So you're able to understand, okay, I have these 8 quantities and which equation works best that I can find these quantities with. So I have here mass, velocity, and another velocity and time. So if they're asking me specifically how much energy does this object gain, that means that, oh, so I'm running this specific distance and this specific speed and I'm gaining speed. So since I'm gaining speed, that process requires energy. And since I have energy and I have speed, I know that I'm dealing with kinetic energy and the work-energy theorem. So here, I am essentially equating work equal to the final kinetic energy minus the initial kinetic energy, and that is 1/2 mv final squared minus 1/2 mv initial squared. So if I just plug those values in, you do get 6,000 joules as your first answer for part A. So yeah, good job. And since this is positive work, we don't have to. Sometimes they might want you to say, oh, there's positive work done on the force, but usually on the object. But since you do have the positive sign, that's also okay. All right. So how do you solve part B? So here it does require a little bit more of intuition. So you want to see what is the magnitude of the constant force. So we know that work is equal to force times distance. So by a little bit of manipulation, the force is equal to the work over the distance. So we have the work from part A, but how do you find the distance? Because we only have the mass, the initial velocity, the final velocity, and the time. So time is a really important variable in this because first we might wonder, I think it's definitely used in part A to confuse you that how do I use time, but it's actually meant for part B so you can understand the relationship to kinematics with this. So you will have to use kinematics to find the distance in order for you to complete this problem. So if we're given that the initial velocity is 10 meters per second, the final velocity is 30 meters per second, and the time is 8 seconds, I first use that first kinematics equation, which is v final is equal to v initial plus acceleration times the time. And if you just plug those values in, you get your acceleration as 2.5 meters per second squared. So now that we have the acceleration, I'm going to go to the third kinematics equation, and I have v final squared is equal to v initial squared plus 2 times acceleration times a change in distance. So if I plug the our new acceleration value and the initial and final velocities, you get x is equal to 160 meters. So now that I have the distance that object traveled and our work, I just have to divide the work divided by the distance, and I get 37.5 newtons. But yeah, good job. That's definitely a question that can definitely appear on the FRQ exam. Sometimes they do like to switch up and put these kind of questions in the MCQ. So a lot of the MCQs will be theoretical, but you're also going to have your good half with these like tiny little these questions, and you're going to have to find or calculate some kind of values. All right, so next I'm going to hand it over to tie everything together before our quiz.
Hey everyone, I'm back to tie everything together, do a quick little overview for you guys. So let's move on to the next slide. So we have our main takeaways slide. This is what you guys should really be taking away out of this cram preview. The work-energy theorem is important because it connects force and energy. So force is going to control acceleration, and it is always related to movement. It's not necessarily conserved, and it relates to work because work is force times distance cosine theta. Energy, it's related to movement or position. It's conserved in a closed system, and it relates to power, which is going to be energy per second. Energy, it's so important to remember that it's conserved in a closed system. You guys will have to use that all over the test, FRQs, experimental design, everywhere. And then your all-in-one useful equation is going to be force times distance equals the change in kinetic energy, because that is the work-energy theorem. And let's move to the next slide. Okay, so we have a practice question for you guys real quick. I'm going to give you guys a couple of minutes and I'm going to put up a poll. Remember, do not put your answers in the chat because I do not want bias happening. Okay, guys? Okay, the poll is up, so make sure you guys take your time to put in your answers. Give you guys a couple of minutes to try and do that, or maybe not a couple of minutes, we're running short on time, so maybe like a minute. Okay, so I'm going to reveal our results, and it looks like out of the 14 or 15 now of you guys that answered, 14 of you guys, or 15 now put D, and 1 of you put E. So let's click and let's see what the solution is here. So, okay, sorry guys. Our answer here is going to be D. It's 4 times as much. In this equation, we're using gravitational potential energy. So the equation for that is going to be mass times gravity times the height, or y dimension where you're at in there. So what we're going to do is, in the question you see a stone is held at a height h above the ground. A second stone with 4 times the mass of the first one is held at the same height. So all we're doing here is we're changing m on one of them from just being m to 4m. Once again, guys, when I told you on the kinetic energy question, if you're getting confused about these, just plug in values. So here, just plug in 1 for mass, and you'll figure out that it's going to be 4 to 1 with your relationship between the two. And that's why our answer is D, 4 times as much. All right, I'm going to pass this off, and we're going to start, or actually, no, I'm in the first quiz, so let's get that going. We're going to put the quiz up for you guys real quick. Okay, so make sure that you guys put this in your browser. If you look in the chat, Steven from Fiveable just put the link in there. So just copy and paste that in your browser, type it into your phone, so you guys can take the quiz and we can interact with you guys live. Okay, so it looks like a good amount of you guys have joined. Let's wait. Now we'll start it because you guys can join after still. So just remember that link is still in the chat. So our first question says, a person leaps out of the plane with a parachute a certain height above the ground. What happens to the total mechanical energy in the system consisting just of the person as they begin to fall? So I'm going to give you guys like a minute to answer this question. And if you guys aren't sure, remember it's better to try than to not try. Okay, so it looks like a good amount of you guys have answered, so let's reveal the answer. So it looks like our energy in the system increased. So I'm going to tell you guys why. First of all, yeah, remember to feel free to ask any questions throughout this. But remember, your system in this is just the person. Yeah, it's consisting just the person as they begin to fall. So why your energy is going to increase is because your system is just the person. It's not the person and the earth, right? Your person that's falling is accelerating due to gravity, and that's why their energy is increasing, because their kinetic energy is increasing because their velocity is increasing due to gravity. So that air resistance. What do you mean by that? Oh, I know what you mean. So in like AP Physics 1, we really don't include that. We're just in like a magical world that we're always just falling without any like resistance. Let's see what else. What did Izzy say? Because the system is just the person. Yeah. Energy is an external force, right? Yes, because it's just the person. Once again, it's gravitational potential energy, but the system is not the person and the earth. So that's why our energy is increasing. If it was the person and the earth, our energy would be the same. So I'm going to pass this on to the next person so we can move on with this quiz. I just want to add real quick before Tammy starts hers. I see in the chat you guys talking about the potential energy decreasing and the kinetic energy increasing. That's only because that doesn't happen because the system is not including the Earth. If the system included the Earth, you would have that trade-off, but we're not including the Earth. So the potential energy is increasing as it's just that's not. You have to like always make sure that you think about your system. Since your system is just the person, you have external forces acting on them, and that's why it's increasing. And give it back to Tam.
All right. So it looks like 75% of us said B, which is the right answer. Great job, guys. For the 25%, that makes total sense. Let's go over this problem. So the question is, when a person lifts a 3 kg bag from the floor to a height of 1 meter, how much work does gravity do on the bag? Okay, so I'll just like go over this question real quick. So the formula for work is force times displacement times cos theta, right? So we're asked specifically for gravity. So we need to be understanding that gravity is the force in the work equation in this place, right? So the formula for gravity is mass times mg, right? Gravity, yeah. Sorry, mg. And gravity is always downward, exactly. So basically what we want to do is we want to do 3, which is the mass, times gravity which is 9.81. And that we will get our force at 29.43 newtons. And once we get that, we can just use that as our force in the work equation. So we know our displacement is 1, and then our cosine is 180 because we're lifting straight up, right? So the cosine of 180 is -1, and that's how we get negative 29.43, or we can round that up to -30. So I see a couple of questions, and this question. Exactly. Izzy is right. You can, the right answer can be positive or negative based on what we define the positive direction to be. In this case, where the gravity is negative, though, right? So the gravity is going downwards. That force is going down. However, the displacement, we're lifting the bag up, right? So we're just lifting it up. And you're right about that. If we define like lifting the bag up as negative, actually it would still be negative, because remember the directions of the vectors are opposite, right? So the displacement is going up, right? Because we're lifting it up, but the force of gravity is always down. So because these two vectors are opposite, the work is going to be negative. Does that make sense? Sorry, took a minute to get there. Okay. Okay, please ask if you have any problem, any questions about it. Yeah. Why is it -30 and not -15? Okay, so for our, when we're finding our force, right, we're doing mg. So that is 3 times 9.8, and that gives us 29.43 newtons. Can you tell me how you got that 15? Then we can talk more about it. We're kind of out of time, so I'll quickly pass it over to the next person. Please write any question in the chat and I will get back to you on it. Let's move on. Okay. So change of plans, because we're slightly over time. We're not going to be covering the rest of the 3 problems. If you want to see more, please consider buying a Cram Pass, where we'll be going over so many more of these problems. So yeah, guys, thank you so much for coming. I hope you enjoyed it. And yeah, thank you for coming, and see you at Crams.